Hello. On the behalf of the Caltech AIAA Student Branch and all of the incredibly hardworking students and advisors below, I have the distinct pleasure of introducing HOMES, the Habitat Orientable and Modular Electrodynamic Shield. Today, we'll be first discussing the problem that HOMES is addressing, as well as the basic concept that surrounds it. Then we'll be discussing exactly how HOMES works. Next, we will go into the verification plan and its results. Finally, we will go into our accomplishments as well as future work. Over billions of years of meteorite impacts and solar radiation has left the moon blanketed in extremely small, sharp, and electrically charged dust particles. The Apollo missions were key in identifying lunar dust as one of the most significant barriers to a sustained lunar human presence. Once inside the habitat, lunar dust can cause adverse health effects in humans. Additionally, dust can pollute agricultural units, food and storage and preparation modules, as well as being liable to damage extremely critical life support systems. To ensure the safe deployment of astronauts in the third stage of the lunar Artemis missions, NASA must adopt highly effective, long-lasting, and adaptable dust mitigation technologies.
In order to solve the problem of lunar dust intruding into habitable spaces, the team devised HOMES. This is a series of tileable panels that leverage and expand upon EDS technology in order to generate a traveling electric field that moves dust. Many HOMES panels can be tiled together to actively clean dust off of floors, workspaces, and other surfaces inside of the lunar habitat. The panels can be connected in any configuration to form a transport system that moves dust to a desired location. In this case, in the bottom right, is a collection panel. This allows for easy dust disposal and decreases the overall circulation of dust in the habitat. Astronauts can easily operate the panels using the control unit. HOMES' high effectiveness, modularity, and low barriers for NASA adoption make it the ideal dust mitigation solution for cleaning habitable volumes and enabling an extended human presence on the moon. HOMES also advances the state-of-the-art of EDS technology through its modularity and scalability, as HOMES is the first implementation of a modular EDS. HOMES is orientable. The panels are rotationally symmetric. That means that they can be oriented to move dust along any direction. It is also very robust, as it can withstand more than an astronaut's weight. It is also very lightweight, each panel coming in at 2 kilograms, and it's very easy to use, as it can be assembled by the astronaut without any tools.
HOMES leverages both the charged and uncharged nature of tiny lunar dust particles with an embedded electrodynamic dust shield. Electrodynamic dust shields, or EDS, are interdigitated capacitors. In a regular parallel plate capacitor, you can see that the electric field goes directly from one plate to the other. However, when you unsandwich these capacitors, you create a fringing electric field, which can exert dielectrophoretic and coulombic forces against both charged and uncharged particles. EDS is typically constructed with long wired electrodes that have varying voltages to create an electric field gradient across the surface. The video shown here is a 2-voltage EDS system on a solar panel. This is evidenced by the fact that the dust is gathering on every other wire electrode, showing that it's going from one high potential to a low potential. EDS has been implemented in optical lenses, thermal radiators, and been used in simulated lunar environments and on the ISS. Literature by and large shows that EDS is effective at removing most dust. However, prior implementations are catered to and embedded in very specialized systems. So what if an astronaut wants to prevent buildup of dust on a larger surface? What if, over the course of a sustained lunar presence, which can be on the order of years, new problem areas come up, and astronauts need a tool to address these issues and mitigate dust accordingly? Our concept of EDS, HOMES, elevates the technology to a modular and therefore scalable realm that can be useful in really any flat area of the habitat. On the previous slide, we saw a 2-phase EDS. However, EDS is not restricted to 2-voltage systems. Electrodes can be supplied with 3 to 4 distinctly varying voltages. On the figure here on the right, where we have plots of the voltages on the wires, each color corresponding to the colored wire on the panel schematic here on the left. As you can see, with the x-axis being time and the y-axis being voltage magnitude, The area with the peak voltage is always moving, and it is moving in a distinct direction across the panel. So not only do we have an induced electric field above the EDS, but we are also creating a moving electric field gradient that can push dust orthogonally along the electrodes, as denoted by the arrow in the schematic. So this four-phase EDS is the basis of our technology, HOMES.
Using HOMES is easy and time effective. In the launch phase, HOMES will be packaged in a habitat compartment on its journey to the moon. In the assembly phase, astronauts will connect the modular panels into an array of desired size and orientation, with collection panels along the edges of the array. End caps can be attached onto the exposed panel edges, and a wired end cap will be connected to the control unit, which will then be connected to a 28-volt DC power supply. HOMES is then ready for use. When the intended activity is performed, dust will fall on HOMES. To clean this dust, all that needs to be done is to change the system power to the on state and turn the EDS switch to the on state. Then HOMES will clean 98.9% of dust in just 60 seconds. In order to reset HOMES, all that needs to be done is to turn both switches to the off state and remove the collection panels and safely dispose of the dust. And HOMES will be ready for reuse.
To ensure that HOMES is a well-engineered system, we set out the following functional requirements and functional assumptions. The top 4 functional requirements were imposed by the Big Idea Challenge, while the bottom 3 were generated internally to the team. HOMES must be able to mitigate dust on the order of 0.5 to 50 micrometers, while presenting a minimal barrier to NASA adoption at a low cost. HOMES must be able to operate from 15 years inside a lunar habitat and able to remove 98% of dust in 60 seconds. HOMES must be operationally easy to use and simple, all the while being rotationally symmetric and modular. We made the following functional assumptions to ensure that we constrained our design process and were able to complete HOMES within the given time requirements. To ensure that HOMES is a properly integrated system, we generated the following electrical requirements and mechanical requirements. Most notably, HOMES must be able to generate 10 Hertz 1 to 6 kilovolt 4-phase square waves for the EDS to work. This is based off of prior implementations of electrodynamic dust shielding for lunar dust mitigation. We further validated these numbers through COMSOL simulations. The rest of the requirements for both subsystems are just to ensure that HOMES is a modular and robust system. Throughout the rest of the presentation, in the bottom left-hand corner, you will see the functional requirements, functional assumptions, and electrical and mechanical design requirements referenced.
The home system starts at the controls unit, which receives power from the habitat and propagates 8 low voltage signals to each of the panels. Each panel has a power supply circuit and an EDS board. The power supply circuit steps up the low voltage signals to high voltage signals to drive the EDS. The panel is supported with a robust mechanical design that can sustain load and impact. The modularity of HOMES is facilitated both mechanically and electrically. Electrically, we have spring-loaded connectors that propagate 8 low voltage signals to each of the panels. Mechanically, we have a very simple magnet and gallopin design that allow users to quickly and easily assemble or disassemble the system. Any number of panels can be connected in any planar configuration. The quantity is only limited by the amount of current that can pass through the controls unit. HOMES is not a concept. The Caltech team has developed fully functional prototypes and has demonstrated the viability of use of HOMES panels and any possible application inside a lunar habitat environment. The next slides provide an in-depth description of all subsystems of HOMES.
Each HOMES panel receives and sends 4 low voltage square wave signals and 3 power rails, 28, 10, and 5 volts. Central to each HOMES power supply is a step-up converter, which takes that 28 volts and brings it up to 3.8 kilovolts in order for the EDS to be run. It was decided to put a step-up in each panel because it would be safer to have low voltage connectors between the panels instead of high voltage connectors. Now, in order to create the 4 high voltage square waves needed for EDS, there are 4 solid-state electronically controlled switches, or MOSFETs. Those use the aforementioned 4 low voltage signals in order to create those high voltage square waves. And now, in order to prevent conduction through the air by arcing, any trace or contact that carries high voltage must be at least 15 millimeters away from any other conductors. Now, those high voltage square waves are sent from the power supply to the EDS electrodes, And because those electrodes are so close to each other, the capacitive coupling causes these dips in the square wave. However, those do not affect dust mitigation at all.
Each panel has an EDS board that is directly connected to the power supply. This EDS board is made up of parallel copper traces, or electrodes, that alternate in groups of 4 through each of the 4 phases, as shown in the image on the right. Since these electrodes are so close together, there is a risk of arcing. In order to mitigate arcing, we tested different configurations of applying conformal coating, just Kapton dielectric, both of those options, or neither of those options, and we found that using just conformal coating was sufficient to prevent arcing. We considered using flexible PCBs made out of Kapton dielectric, a material that is known for its ability to prevent arcing at high voltages. However, we found that it was very expensive to manufacture them, and they were actually worse at preventing arcing than conformal coating was. The control unit enables users to modulate the activity of homes. We assume that the habitat outlet provides 28 volts DC to power the system. There are then 2 switches that the user can use to control the system. The first is a power switch that powers all low voltage components, and the second is an EDS switch that activates the high voltage EDS system. When the power switch is on, the Arduino microprocessor then propagates and delivers each of the 4 phase signals to the adjacent panel. The power signals are sent in a similar fashion. Note that dust will not move unless both of these switches are on.
To complement the electrical requirements, Holmes's mechanical design focuses on the physical, vibrational, and thermal protection of the electrical components. A 4.5 millimeter peak plate protects the power supply PCB when the panel is under load. The power supply PCB sits on flexible standoffs 3.3 millimeters away from the walls to vibrationally isolate it and prevent damage from shaking during launch. The thermal management system conducts heat away from the potentially hot step-up converter through a thermal gap pad to the wide aluminum plate that acts as a heat spreader. For the materials, we prioritized performance and easy manufacturability. PEEK, an aerospace-grade plastic with a high dielectric constant, was used for the housing to protect and not interfere with the EDS. A readily available aluminum alloy was used for the heat spreader for its low density and high conductivity. Holmes also leverages an aerospace-grade adhesive with low outgassing to prevent damage during launch for a total weight of 2.1 kilograms. Lastly, both the end caps and collection panel have been prototyped in PLA. This satisfies our design requirement of all materials having a low barrier of adoption for NASA. And here we have a video of 2 panels being connected. You can see my hands for scale. The embedded magnets in each panel are strong in tension to allow for easy assembly and weak in shear to allow for easy disassembly.
We can see on the side view of the Holmes panel the magnets, dowel, and slots that allow for the easy and accurate assembly of panels as previously demonstrated. One of the main challenges of a fully scalable and modular EDS implementation is inserting a reliable, robust electrical connection between panels. Spring-loaded pin connectors on each side of the panel were used to fulfill this requirement, all the while remaining compatible with Holmes's mode of assembly. To ensure compatibility across all panels, individual electrical connections within each pair of pin connectors, so the 28 volts, 10 volts, 5 volts, common ground, as well as all 4 Arduino signals, were placed in a consistent yet rotationally symmetrical layout as portrayed on the bottom left. As seen on the right side, these pins were then connected via wire harnesses and latching connectors to each power supply PCB. These connectors were then further secured to the PCB with Loctite in order to protect the integrity of electrical connections during Holmes's exposure to various loads and vibrations. The electrical connections from pin to PCB were also tested for each pin prior to and following the panel assembly process in order to further guarantee a reliable electrical connection between panels during use and testing of Holmes.
There are 2 main accessories which facilitate the ease of use and practicality of Holmes, the end cap and the collection panel. The end cap is a feature that can be attached to any exposed edge of Holmes using the same magnets that are on the panels. This feature acts as a physical barrier to prevent dust accumulation on the spring-loaded connectors. The collection panel is another feature that can be attached to any end cap in a desired location, most practically at the end of the dust migration. The collection panel has a central cavity with a 60-degree slope that accommodates for the lunar dust angle of repose. The main functionality of this feature is to catch any dust that is pushed off the home's panels. The collection panel can be easily removed later for disposal of dust, as however the user sees fit.
The goal of our verification program is to qualify homes to a technology readiness level of 5, which consists of assembly validation in a relevant environment. To accomplish this, we conducted a variety of electrical and mechanical tests. These electrical tests included dust locomotion testing, high potential testing, and accelerated lifetime testing to verify the functionality of the EDS system in both the short and long term, characterize the arcing thresholds of the EDS PCB, and characterize the dust removal effectiveness of the panel. The mechanical tests include load testing, impact testing, and vibration testing to ensure that the panel can survive the obstacles encountered in the lunar habitat environment, such as the load of an astronaut standing on the panel, a suddenly dropped tool, or the vibrational loads encountered during launch and landing on the lunar surface.
The quasi-static spherical loading test was done to ensure that homes could withstand the weight of an astronaut as well as the gears standing on top of homes. To simulate the worst case scenario, we applied a point load to the middle of the top plate while supporting the bottom face of homes with a flat plate, as it would be in its normal use case. The 441 Newton load was calculated by taking a 100-kilogram astronaut, an 81.5 kilogram spacesuit, multiplied by 1.5 times dynamic loading factor for walking. We then multiplied all of that by the acceleration due to gravity on the moon. We then applied this load for 16 seconds and hit even a little bit above the 441 Newton threshold. After this test was concluded, we inspected the area of impact and found no visible damage. Additionally, we ran dust over homes and ensured that there was no impedance to its dust moving capabilities, thus showing that homes passed the quasi-static spherical loading test.
The impact test was conducted to simulate a situation where a point load is applied suddenly to homes. This test was conducted using the custom homes impact rig seen in the image on the right, which consists of a rounded impactor mounted on dual linear bearings, which was dropped onto the EDS PCB. The integrity of the panel was continuously monitored during impact by measuring electrical continuity of the traces in the area of impact. From this testing, it was determined that the panel functionality was maintained up to a drop height of 75 centimeters, which, using the mass of the impactor and differences in gravity between Earth and the lunar surface, was determined to be equivalent to a 25 centimeter drop of a 100-kilogram astronaut on the moon. In the images on the left, you can see a microscope image of the panel before and after impact, which shows that there was minimal cracking after impact, and this cracking did not affect EDS functionality.
The random vibration test was conducted to ensure homes meets NASA's minimum workmanship criteria for electrical, electronic, and electromechanical components. This test can identify latent defects and manufacturing flaws in electrical and electromechanical hardware at the component level. We conducted this test using a shaker table provided by Professor Sergio Pellegrino at Caltech. This test was conducted along 3 orthogonal axes using the mount shown on the bottom, with an accelerometer mounted a couple millimeters away from homes. The minimum workmanship random vibration levels that were used for the test are shown at the top of this slide. The shaker table was ran such that the acceleration measured by the accelerometer matched the levels in the table as close as possible, and this was done for 1 minute along each axis. Before and after the test, the functionality of homes was evaluated, and we determined that the random vibration test did not affect the functionality. So homes successfully passed the random vibration test. Before flight, homes would need to be tested at flight qualification random vibration levels, instead of the minimum workmanship levels that we used for this test. We attempted to perform the qualification test with this shaker table, which was the only one we had access to, but the shaker table was unable to reach qualification random vibration levels, so we weren't able to perform the test with qualification levels.
The purpose of the accelerated lifetime test is to determine the electronic lifetime of homes and observe Holmes's reaction after running for an extended period of time. Holmes has been running for about 100 hours. Since we are not letting Holmes rest, this is an extreme overtest of what the electronics will actually be expected to do on the moon. We approximated that Holmes will be used for about 460 seconds per week in the Artemis base, which amounts to an average of about a minute of use per day. With this assumption, Holmes will be able to run for at least 15 years on the moon.
With this continuous cycling, we have been monitoring the temperature of the control unit and homes to make sure it isn't overheating. After these 100 hours of cycling, homes and the control unit have not exceeded a temperature of 60 degrees Celsius, which is an incredible result. Since the temperature has not been increasing, we are confident that we will be able to get to our goal of simulating at least 30 years of use on the moon. The dust test is supposed to qualitatively show us whether Holmes is pushing off approximately the same amount of dust after continuous cycling. We constructed a rig that will pour about the same amount of dust in the same location every time we conduct a dust test for consistency. We have also attached a GoPro so we have a bird's eye view of dust particles being pushed off. As you can see from our videos, Holmes is just as effective at pushing off dust particles after 100 hours of continuous cycling when we compare it to the video before we conducted continuous cycling.
To prove that Holmes is truly modular and able to move dust in any direction, we set up 3 panels, each 90 degrees rotated in plane with respect to the next. You can see the LSH-1 or Lunar Highland Simulant 1, the highest fidelity lunar dust simulant available, is moved in a matter of seconds and deposited in the collection panel, thus proving the simplicity, dust mitigation properties, and the modularity of Holmes.
We also quantitatively evaluated the dust removal efficiency of Holmes using built-in image analysis tools in Mathematica. 2 trials were completed, one with visibly coarser dust and one with finer dust. A microscopic camera was used to photograph the panels before and after 60 seconds of running Holmes. On the figures on the right-hand side of the screen, there are 2 sets of images, one for each of the trials completed, showing the before and after photos of these experiments. For both trials, we first looked at particle counts, as noted by these 2 plots here, where the y-axis is particle counts and the x-axis is particle diameter bin sizes with a log scale. And we immediately noticed that for both coarse and fine dust populations, the particle count dramatically decreased. We then decided to look at the total surface area covered by the dust on the panel. And we found that for both trials, more than 98% of the total area previously covered by dust was cleared. In the particle size range that we are most concerned with of 0.5 to 50 micrometers, we found that over 96% of the surface area previously covered by dust was cleared. And so this confirms the efficacy of Holmes and shows that Holmes satisfies the dust removal and dust mitigation functional requirements.
This summary table shows that Holmes passed each of the verification tests, except for the accelerated lifetime test, which is still currently ongoing. The success at Holmes in passing this verification test demonstrates panel functionality within the set environment of the lunar habitat.
Holmes has successfully achieved the goals initially laid out of scalable modular EBS. This versatility allows for Holmes to be used on a variety of surfaces in the lunar habitat. Holmes has been shown to reliably remove over 98.9% of dust in 60 seconds and deposit it into the appropriate collection location. Furthermore, Holmes is mechanically reliable, having passed load, impact, and vibration testing, and is currently undergoing lifetime testing to achieve TRL5. Holmes has met all of the functional requirements initially laid out and offers a promising proof of concept for dust mitigation in lunar habitats for the NASA Artemis missions and beyond. Looking at the functional requirements initially outlined at the beginning of this presentation, we can see that the majority have been fully verified through testing. The only ones that remain to be fully verified are the low barriers to national adoption and lifetime. Our accelerated lifetime test is currently in progress, and our panels currently have low mass, size, and cost, so with a few modifications, they can be easily adopted by NASA.
There are a few tasks to be completed before Holmes is fully space ready. These include protecting the surface of the EDS PCB with an abrasion-resistant spray coating of a high dielectric strength, such as an alumina ceramic, through a process called magnetron sputtering. We will also print an arrow on the surface of the EDS PCB to indicate the direction that dust will move for ease of use. In terms of testing, we must perform more rigorous random vibration testing and potentially design packaging to protect Holmes during flight. We must also perform a few more months of lifetime tests. Looking to the future, there are a few different ways that we can expand the use cases of Holmes. We can reduce the size, weight, and power by first designing a custom lower profile high voltage DC-DC converter to reduce the size and weight of the panels. We can also replace the Arduino in the control unit with its own dedicated circuit or smaller microprocessor, resulting in a significantly smaller and lighter control unit. We can also reduce the power draw, perhaps through modifying the power supply circuit to be a half-bridge circuit. Another way to increase the number of use cases for Holmes would be to develop a more robust thermal solution for use in a greater range of environments, such as in the airlock or on the surface of the moon. We could also change the material, electrode layout, voltage, and frequency, among other specifications, to allow for Holmes to work in a multitude of different environments. Notably, one potential application for homes could be on the Martian surface. In general, preliminary indications show that the designs for the lunar environment are applicable for the Martian environment as well. In order to make homes compatible with the Martian environment, modifications to electrode spacing, frequency, and voltage could be made, and we could bring the benefits of homes to Mars, supporting a sustained human presence and future scientific advancements.
We would like to thank the Big Idea Challenge and Caltech for this opportunity, and the NIA and Space Ground Consortium for funding. We would also like to thank our mentors, Dr. Chung, Mr. Abid, Dr. Elachi, Dr. Mello, Dr. Kastner, and Dr. Arya, and all the contributors who helped make this project possible. Thank you very much for listening.